In this video, we're going to see how the product rule helps us to differentiate functions that seem to have two main expressions multiplied together. If we go back to our standard way of differentiating a function, when we see a function, as in our first example here, find the derivative for y equals x plus 5 in brackets with 2x, take 1 in brackets. The first thing we think to ourselves is, okay, we're going to have to expand this function so that we can differentiate each individual term. So we would go ahead and then differentiate as required. However, when we're dealing with functions where we seem to have the product of two parts, we can use a more efficient approach called the product rule. And basically, when we have these two functions that seem to be multiplied together that create one function, we can find the derivative by doing the following. We can write down the first times the derivative of the second, plus write down the second expression involved times the derivative of the first. As we get used to writing this rule, it will become a little bit more easier, but this is something that I always say to myself as I'm using the product rule. Write the first times derivative second plus write the second times derivative first. So let's see if we can put this into action with our original function that we had in our situation and see if we get a derivative of 4x plus 9. Okay, so we're going to write the first function times the derivative of the second function, so the derivative of 2x take 1 is 2, plus write the second function times the derivative of the first function, and the derivative of x plus 5 is 1. We've simply done the differentiation. We can see that we can collect some like terms here, so we can neaten this up a little bit and recognise that we in fact get 4x plus 9. Let's have a look at another example. We've got y equals 2x squared multiplied by x plus 1 all squared. So we can see here that we actually have those two expressions multiplied together. What we'll also notice in our second part of our product here, we have a situation where we have a power greater than 1, so perhaps we can also bring in the idea of using the chain rule here in its quick and easy way. So let's find the derivative. We're going to write the first times the derivative of the second. So when we're differentiating a bracket, we know we bring the power out, so we differentiate the bracket by reducing the power to 1 times the derivative of what's inside. So we're going to have 2x plus 1 to the 1 times 1, plus write the second times the derivative of the first, which is 4x. Just put a line there to separate that. Okay, now essentially when we're asked to use the product rule to differentiate, all we have to show is that we've used it. But often we do want to simplify how our derivative looks, because often we're maybe trying to find some stationary points of a function or trying to maximize a situation. So I am going to neaten this one up a little bit. I'm just going to take this first part here and neaten that up. So I can see I've got 2 times 2, which is 4x squared outside a bracket of x plus 1. And in the second part here, I can just bring that 4x to the front, and I've got x plus 1 squared. Now we've been asked to differentiate using the product rule, then this would be the solution that we would present, and there's no real need to simplify it. But sometimes we're using the derivative to find the stationary points or the gradient value at a point. So sometimes it is really nice to be able to simplify what we're looking at. Simplifying in this situation would be taking out common factors. So within our two terms that we've got here, we can see some really nice common factors. We could take a common factor out of 4 and an x. So I'm going to pop that out the front. And we can also take a common factor out of an x plus 1. So now what we've got left here is just an x, and in our second term we've got one of these brackets. So when we simplify this derivative, we've got 4x outside of x plus 1 outside of 2x plus 1. So now it's your turn to have a go at differentiating the following functions that have more of a product look, where we've got two expressions multiplied together. So where we can use the product rule to make differentiation a lot more efficient. So have a go at question 5, straightforward use of the product rule. In each case, if you can, see if you can do some simplification by collecting any like terms. And in question 6, you're asked to determine the stationary points of the function y equals x plus 2, take minus 2 bracketed with 2x take 3 all squared. So again, we're going to use the product rule. We're going to find the derivative, and we know that when that derivative function represents the gradient equaling to 0, we want to find what x values that occurs for, and then find the y values that go with each x value to actually identify each stationary point. So go back and have a go at the questions 5 and 6, and pause the video at this point to have a go, and then come back and have a look at the solutions. Okay, the solutions to question 5a. Looking at this, we've got two expressions multiplied together. So when we do the derivative, we're going to write the first, derivative of the second will be 3, plus write the second times the derivative of the first, which is 1. So we could simplify this as 3x plus 18 plus 3x minus 2. So we've got 6x plus 16. Solution to our second example here, we've got write the first, diff the second. So we're going to differentiate the bracket. So it's going to lose a power to 3 times the derivative of what's in the bracket, plus write the second, diff the first. So simplifying this, oops, we've got 16x out of x plus 2 cubed plus 4 out of x plus 2. Oops, just a little error there. Okay, so we can take out some common factors. And have a solution of 4 with x plus 2 cubed and 5x plus 2. In our final example, determining the stationary points of the function, so we'll differentiate to find the gradient function. Just neaten this up a little bit. Okay, we want to know when this equals 0. Now we could pop this into our class pad and press ask it to solve the situation. We could also expand it and simplify it further ourselves, but what we should come down to is x equaling 1.5 or x equaling 1.83 recurring. So the stationary points is 1.5, and when we substitute 1.5 back into the original equation, we get 0 and 1.83 negative 0.074 all recurring.